Hello folks, this is 2023 May-June paper 2 and the question number is 2. It is concerned with various chapters because it has a combination of forces where you can see a beam like this, and in another page we have some sort of knowledge required for projectiles as well. So the question says, what is meant by the center of gravity of an object? So we know that we are not going to the definition part. Let's go to the problem part. It says two blocks are on the horizontal beam that is pivoted at its center of gravity as shown in figure 2.1. So this is the horizontal beam or bar. We have got two blocks here, two blocks, and it's pivoted at the center of gravity here, CZ here, as shown here. A large block of weight 54 Newton is a distance of 0.45 meter from the pivot, here, shown here. A small block of weight 2.4 Newton is at a distance of 0.95 meters from the pivot, and a distance of 0.35 meter from the right hand end of the beam. So it is this thing is a distance of 0.3 meter from the right hand of the beam. The right hand end of the beam is connected to the ground by a string that is at an angle of 30 degree to the horizontal. The beam is in equilibrium right now. So by taking moments about the pivot, calculate the tension T in the string. So we have to take this as the fixed point, and by taking moments or torques about this point, we have to find the tension. So what happens here is, here tau anti-clockwise, that's equal to the anti-clockwise moment is given by this weight, because pivot is here, the weight is here, it will try to move the bar like this. So this anti-clockwise is given by 54 into the distance here, which is 0.45, and since the angle is 90, we don't have to use that, it's equal to 1. Now tau clockwise is equal to, this clockwise moment is given by this weight, because it tries to move it like this. So it is 2.4 into the distance from here to here is 0.95 plus another is the tension force T here. This also tries to move the thing in clockwise sense. So that's, it's also contribute to the clockwise moment. So it should be equal to T into the distance from the center, which is 0.95 plus 0.35. It becomes 0.95 plus 0.35 becomes 1.30 meters. So it is 1.30 into sine of angle between direction of force and R. Sine of angle between direction of force and R. So we can use the smaller angle here. Even if we use this angle, things are okay. It's because sine 180 minus theta equal to again theta. So we can use sine this angle or sine this angle 150 also. So it is sine of 30 degrees. So now since the system is in equilibrium, these two should be equal. So we must have tau clockwise equal to tau anti-clockwise, which means T into 1.30 into sine of 30 degrees is equal to 54 into 0.45. So this will give us T is equal to, so let me do the calculations. 1.30. So this comes to be equal to 33.9 newtons. So it is 33.9 newtons. Now the string is cut. So this string is cut here, so that the beam is no longer in equilibrium. So what happens now is, if the string is cut, definitely it seems so to me that this beam will be like this, come like this, it will go like this. Calculate the magnitude of the resultant moment about the pivot acting on the beam immediately after the string is cut. So now this thing is absent, so only this and this remains. So the resultant torque resultant is equal to, I assume from my insight that this one is more than this one, so that's why I'll do it as tau A minus tau C, that's equal to 54 into 0.45 minus 2.4 into 0.95. It will give me So 22 point some zero something like that. So I'll write it as 22 Newton meters. So it is 22 Newton meters. This is tau resultant. Now we have to go to next page. So next page has this. So I'm directly doing it from the questions that arrived at our center from the board itself. So let me turn the page. I'll have to do some manipulations here. So yes. So making videos is definitely a very difficult and arduous task. We have to fix so much things which do not appear in the camera. Just like when we see movies, we blame actors like that. So here also, we are like actors, and people blame us a lot. Actors do get their benefits, but we don't actually. Okay, so now things seem to be fixed. Now it says the beam in B rotates when the string is cut and the small block of weight 2.4 Newton, which is at the right, is projected. It is thrown into air through the air. Figure 2.2 shows the last part of the path of the block. So it is projected like this, and it comes like this before it hits the ground at the point Y. So it is jumping like this. At point X on the path, the block has a speed of 3.4 meter per second. So the speed here is V equal to this much. And it's at a height of 1.58 meters. So let me say it as Y. Above the ground. Air resistance is negligible. So a sensible assumption. Calculate the decrease in the gravitational potential energy of the block for its movement from X to Y. So we need to find the change in the gravitational potential energy. So it is delta in GPE is equal to PE at X minus PE at Y. That's equal to mg into Y minus 0 simply. This mgy is mg equal to 2.4 Newton and this g is equal to 9.81. So this is the delta GP. So when it recalculations, it is equal to 4.32 joules. So it is 4.32 joules. Now use your answer to C1 and conservation of energy to determine the kinetic energy of the block at Y. So the conservation of energy means that we must have potential energy at Y plus kinetic energy at Y should be equal to potential energy at X plus kinetic energy at X. Yes, so we should have, or we need to find the KE at Y. That's why KE at Y should be equal to PE at X minus PE at Y plus KE at X. So equal to, this will be equal to, so this gives us KE at Y is equal to, this difference is equal to 4.32. This is 1 by 2 mass into V squared equal to 4.32 plus 1 by 2. The mass is equal to weight by the value of G 9.81. The value of V is 3.4 squared. So this gives us, so it is 0.5 into 2.4 into 3.4 square divided by 81 equal to plus 4.32. So this is 5.73 joules. So it is 5.73 joules. We don't have to write joules here. Now state the variation, if any, in the direction of the acceleration of the block as it moves from X to Y. So no variation, because there is no variation at all. It is simply the value of A is equal to Z, which is acting downwards. Because in a projectile body or body in a projectile motion, the only force is the force of gravity. The only force is the force of gravity, which acts downwards. Now again, need to turn the page. So last portion remaining here, last portion. Okay. the last person say the block passes point X at time Tx and arrives at point Y at time Ty. So we have got a clock set there. The clock records time as Tx and Ty. On figure 3.2, sketch a graph to show the variation of the magnitude of the horizontal component of the velocity of the block with time from Tx to Ty. Numerical value is not required. So simply it is so simple that the horizontal component of velocity does not change. It is constant. It is constant because there is no force in the horizontal direction. So that's why the graph should be, since we don't require any numerical values, we can draw a simple straight line parallel to the time axis. Simple straight line parallel to the time axis. Okay, this finishes the solution to this question.